First of all, guys, I got the. I don't know if my camera's going to focus in or not. It's not doing such a good job, is it? Okay, there we go. Uh, I finally found a. So we have two types of Hall effect sensors. We have what they call a switch or a digital Hall effect, and we looked at that, right? Right. Yeah. So a digital Hall effect, if we come in with one polarity, it turns it on. If we come in with the other polarity, it turns it off, right? So it latches it, it stays latched until we come in with the opposite polarity. This is an analog. Okay, one polarity does what? Sorry, turns it on. The other polarity turns it off. Can you see what I'm doing? All I'm doing is swapping the magnet. So it's a switch, so it stays latched until we do what? Until we bring the other polarity. I can bring the same polarity up all the time and nothing happens. Well, we can make it appear to work like this. So if I come over like this, it turns on, it turns off, it turns on, it turns off, because what it's doing is seeing the swap in the direction of the lines of force, right? You understand? Yes or no? So see, it turns on, then I come away from it, turns off. So this is basically what we use on like pneumatic cylinders when we sense the position, whether it's fully extended or fully retracted. This is an analog sensor, which my camera went out of focus again. So on the analog sensor, so what an analog sensor does, it gives us a voltage that is proportional to the, it gets a voltage that is proportional to the magnetic field. So y'all can read that, right? Okay, so we'll move it over a bit. So right now it's not sensing a magnetic field, and this is the one right here which you can't see because my camera won't focus in on it. Still won't. So what I'm going to do here right now is show me 1.31 volts, and I'm going to come in with one polarity. We could look it up. And I want you to know, I'm going to come over here and just start bringing this in. And you can see it's already started to pick it up. Say it's 1.33, and I come over here, started to pick it up. And notice when I come in this polarity, I'm coming down toward the Hall effect, then the voltage does what? It goes down. I'm going to flip polarities, and I'm going to start bringing it down. And what happens? Now the voltage goes up. So this guy can sense a north or south field, but it can also detect the strength of the field. That makes sense. So Hall effects, we use this quite a bit for speed sensors, and we'll show you all that. But what does a Hall effect do? It don't sense metals. It senses what? Magnetic field. We know what a sensor is now, right? So what's a sensor? Yeah, the second one is probably what we're going to use more often. So what is it? A device that converts a physical stimuli into an electrical equivalent. We have two broad categories. We have analog and digital. Everybody understand those? So we went through all these controls. We've already looked at position. We've looked at proximity. So what we'll look at now is speed. And of course, speed is how fast something is moving, right? So speed sensors, these are not all of them. These are just ones we look at. We have what we call a tooth rotary encoder or sensor. We have a Hall effect, which also could be a magneto-resistive, guys. You don't really know because they basically do the same thing. We're going to have DC generators or tachometers. We're going to have direct current generators and then AC generators. And then, of course, our incremental optical encoders. Optical, I'm going to redo that. It won't let me delete it. Very unusual. My keyboard is not working. Incremental encoder, we have two. We have optical encoders, incremental encoders, and also we have Hall effect or magneto-resistive encoders. And like I said, you know the difference. Usually the magneto-resistive is a little bit more sensitive than the Hall effect. Basically, it's how they sense the magnetic field. So this is one thing that we can do. This is very popular with checking the speed of motors. So you know, we tell a motor to run a certain speed. It's always nice to have the ability to see if it runs it. Well, a strobe attack, which I made one of those. A strobe attack basically flashes a light at a certain speed, and when the speed of the light and the speed that this thing is rotating, when they match, what happens? Y'all see this every once in a while. It's sort of every once in a while. Uh, People taking videos. Some people don't understand videos too much. They're flashing and snapping pictures, literally. And you've ever seen those movies where it looks like a wheel on a car is running backwards, right? Or it looks like you're stationary, but what it's doing is you're seeing what we call the strobe. Used to time a car. That's what we use. We use they call it timing light. So what we would do is we hook it up to the number one spark plug in series with it, and every time they fire that spark plug, it generates light. And then you got a mark down on one of your wheels, and you have a line that you line up, and you can set the time of the car. Now it's all set electronically, right? So what's happening is when that light flashed, everything appeared to be stationary. We had one of our guys work out there. We were timing his car at night. Most of the time you had to do it late because the light wasn't bright enough. And we were flashing that thing. It looked like the fan was sitting still. Because it would flash it, and the fan was sitting still. And Jerry said, "Hey, my fan is not turning." And guess what he did? He stuck his hand down. Boom! I get his hand off my coat. So what? What you do is you take that and take that wheel and put it down on the shaft of your motor, and when it spins, it causes the axle sensor to spin. And it basically just does what it is. But we don't have the batteries for it. One of them you press down, one of them is a hold button, so you make it hold, so you pick it up and read it. Does that make sense? No, that's the new spot. Now the problem with this guy is that basically if you got an extremely low torque motor, this guy actually it's going to create a little friction on the motor. So these little DC motors we can use, right? But a big motor, you know, it really is. These would be non-intrusive, so these guys right here would not even generate any friction at all. And sometimes they work on a flat surface, so a lot of little motors will have a flat side where you screw a key down in, and a lot of times you can use that instead of using the tape. But what you do with a strobe attack is you come up here and you turn it and you change the frequency of the pulse rate, and when your motor looks like it's stopped because it's not, then you can read, which is pretty interesting. We used to have one around here, but I can't find it. But I made one using but it's over another class. So this is one guy. This works out like this is a variable reluctance encoder. So what determines how much EMF we can get by an induced voltage? Yeah. Good. Keep going. Yeah, when we take a break, I'm about to restart my computer. My stuff's not working on here. So what happens here is we've got a sensor. It's nothing but a magnetic field. And then what happens is each one of the tooth flies around, it causes the magnetic field to concentrate through the tooth, right? You understand, which causes it to create a little pulse into this little transformer that's around the side. Now we have motion, right? So the magnetic field is sitting there not doing anything. When the tooth comes around, it concentrates to it, causes the magnetic field to concentrate to the tooth, which causes motion. So we get a small little pulse out of this little thing, this little transformer line right here, this little coil. This is used a lot on variable reluctance sensors. We have different ways that we. So the new thing we have used to, we had a big problem with when we slammed on our brakes on a car. What happened? That lock up and then you lose control of the car. What did we go to? We went to anti. How do those things work? Well, what you're doing is it senses that the car's in motion and your wheels are not turning. Well, how does it know your wheels are not turning? It's got a sensor out there. We have different types. One of the most popular is this guy right here, variable relationships. Oh, this thing on your wheels, variable. It's very, very rugged, no moving parts. It does not have to be powered, right? You understand? So this is really sensing when a part is moving and the wheels have stopped. So good question. So we use these on analog brakes. We used to have a set around here, but I'm not going to tell you what the story behind that. That uses variable sensors. It was a speed control system that we had on a DC motor, and of course, this was a sensor that you could actually see the tooth gear. It was just like a gear. Any gear we could use this just seems right. Understand? Any gear. It doesn't have to be a special gear. Also, got to be a metal gear. It can't be a plastic gear. But we can use this just about anywhere to sense the speed of a car. So they might be using this guy to sense the speed of your car for your speedometer. Everybody okay? So this is just a typical one, very, very rugged. Most of them that you see on cars are going to be encapsulated in plastic, and all you'll usually see is just the end there. And it's usually on the inside. Hall effect or magno-resistive, we don't know these things. These work on exactly the same principle. The sensor itself has a magnet behind the sensing element. So the magnetic field passes through the sensor, right? You understand? And every time a tooth comes around, what does it do? It generates a pulse for every tooth. Okay. And then we can count the number of teeth, and we can use that to figure out what the speed is. Then we can have two of them, two Hall effects, offset by 90 degrees. And then this will give us a quadrature encoder, but it doesn't use light. So this is very popular. These guys don't care if it gets dirty, right? Understand that? So this is the encoder that's used inside. What is it? Inside this. I think we ran this the other day, right? Did we show y'all? Did we do that in this class? So this is a geared motor. Did we look at this? Yeah, you have to. We didn't calculate the speed, do all that thing. Yeah. So this is a Hall effect encoder. I don't know if I get the back off of it or not. In fact, it won't hurt. Okay. So all this is when the motor turns, it spins this magnet, and then circular magnets usually go north south, north south, north south, north south, and it comes up and turns it. And here's our Hall effects right here. So that's the way this guy right here is working. So this is not an. What advantage does using an Hall effect encoder have over a optical encoder? Probably not more accurate. It can work in a more harsh environment, right? So optical encoders, we got to make sure. If we went over and looked at the robots, those optical encoders, they're enclosed. Got a seal around them and all kind of stuff to keep watt from getting in there. It does, yeah. I think the guys from Rosa said one of the things they have to do is go out and clean the encoder. I mean the optics on out there every once in a while. Well, it's a job. If it wasn't having, if it wasn't for having, if these things fixed themselves, guys, a lot of us wouldn't have jobs, right? So we call that preventive maintenance. Next thing we have is these are very, very popular, especially in older machines. And this is that guy right there. These are what we call tach generators. We have two types. We have, so what determines how much voltage we get out of a magnetically? Yeah, but it's what number of loops, right? You understand that, right? The strength of the field, and then speed of the motion. And the output is proportional to the speed of the motion. So what that means, if you double the speed, the output of the generator doubles. If you half the speed, the output speed. So if I know the voltage at a certain speed, then of course it's a linear curve, then we can calculate the speed from the amount of voltage we have. That makes sense? So I usually put an encoder on here. So here's my MG set. Y'all ever heard of an MG set? That's a motor generator. So it's a motor that has its purpose in life is to run a generator. So all I have here is I have a motor turning a generator. They're basically the same thing. What's nice about a DC motor, most of the time you can also run the motor as a generator. These are permanent magnet motors. So usually the tach generator uses a permanent magnet. So that means the strength of the magnetic field is fixed, right? You understand. And then, of course, the number of loops you don't have any control over. They're inside the thing. So what is going to be the output of the tach generator is strictly going to be controlled by what? The speed, right? And I don't think that little so now if we increase the speed, the what? The voltage goes up. Can't say more power. So if the motor's not running at all, we get 0 volts out. So if I knew the speed of the motor right now, right, by using some other type of tachometer, once I know the speed of the motor, then we could calculate the volts per RPM. We okay? In fact, that's what the little piece of tape is on there. So I could my little strobe light. I need to find that. My little strobe light. When this guy looked stationary, that meant my flash rate was the same as the speed. So DC tack generators, you're going to run into those on older equipment. We have other ways we can do that now. But these things, these are all over US Steel, these DC tack generators. And they are perfectly linear. What do we mean by linear? Yeah, so the voltage varies directly proportional to speed. So this would be, if we knew the speed, so here it says 6,000 RPM, we get 23 volts out. I'm sorry, these are 2, 4, 6, 26 volts. No. Okay, that's 1. This would be 23 volts. And so 0 here, so if I've got 6 volts out, that means it's running at what? 2,000 RPM. Don't say power, guys, it's voltage. What determines the amount of power? Yeah, V times I. So we don't know the power. So we get more voltage out. It all depends on what type of load you're getting in here. So the voltage varies proportional to what? Speed. Okay, guys, y'all go ahead and take a break. We'll try to get my computer working again. That would be interesting to bring into a PLC.